Welcome to Module 1 of the Megit Sensing Systems Industrial Vibration Training course, Vibration and Types of Monitoring. In this module, we will cover what is vibration, causes and effects of vibration, how to detect vibration, and different types of monitoring. Let's begin. Vibration is the forced oscillation or the back and forth motion of a mass in a spring mass system in equilibrium about a stationary reference point. In this case, in our example, the stationary reference point is the shaft of our rotor. Vibration can be characterized using three specific components: frequency, amplitude, and phase. Frequency is defined as how many times an event repeats itself in a given period of time. It is defined in cycles per second or hertz, but is also commonly referred to in cycles per minute or rotations per minute. A complex time signal is made up of several discrete frequencies which can be separated using a fast Fourier transform or FFT process and then used to identify the cause of the vibration. Amplitude is simply another word for amount or quantity. In the field of vibration, amplitude is characterized in three interrelated ways: displacement, velocity, or acceleration. The amplitude readings provide an indication of severity for a particular problem. We can express how much movement or vibration is occurring by measuring the distance being moved, or displacement. Displacement is a measure of how far the structure is moving from one extreme to the other. It is usually expressed in terms of mils peak to peak. Displacement is normally used for assessing severity on machines with journal bearings. Displacement can also be used on equipment with roller element bearings rotating at less than 600 cycles per minute. Displacement should not be used for severity assessment on machines with roller element bearings running faster than 600 CPM. Velocity can be defined as a change in displacement over time. It is usually expressed in terms of inches per second. Picture a body in oscillation, like the back and forth movement of a pendulum. The velocity is constantly changing. At the midpoint, when the pendulum is perfectly vertical, the velocity is at its maximum. At the point of maximum displacement, when the pendulum is at the extreme outer edge, the velocity is zero just before moving in the opposite direction. Velocity is the best assessment of severity for the frequency ranges between 10 Hz and 1 kHz. Most vibration measurements are collected and stored in velocity. Acceleration can be defined as the change in velocity over time. It is usually expressed in terms of g's. Acceleration can be roughly considered a measurement of force. Acceleration is most useful in evaluating severity at frequencies above 1 kHz. Acceleration is also very useful in evaluating impacts or events of short duration, such as a defective bearing when the balls of the bearing come into contact with the defective portion of the bearing race. Phase is a measure of how one body moves in relation to another body or to a reference, and is usually measured in degrees. Phase provides us the ability to distinguish between faults that show a similar frequency response. It is commonly used with balancing applications. There are many causes of vibration, including mechanical defects, such as bearing damage or broken gears, mechanical conditions, such as resonance or misalignment, and electrical conditions, such as electric motor defects. Vibration can have negative effects on equipment. The expended energy from vibration causes wear of components, reduced performance, increased energy consumption, and reduced reliability. Vibration can also excite natural frequencies, causing significant vibration at the components. Vibration is typically detected using an accelerometer. The accelerometer is comprised of a piezoelectric material that creates a small voltage when excited by vibration. This voltage is the input to a data collection system, typically in millivolts per G. This signal is then digitized and signal processing is performed to provide the desired measurement output. The measurement can be a time waveform, overall vibration measurement, or an FFT. There are several different types of vibration measurements. The most common are overall vibration, time waveform, spectrum or FFT, and specialty measurements such as peak view or enveloping. Each has its uses and often can complement each other when used together. We will discuss this in detail later. Vibration analysis can be effectively used to monitor all sorts of machine problems. Because most problems have specific characteristics, by performing frequency analysis, we can differentiate between the various problems. Unbalance, misalignment, looseness, and bearing defects are just a few of the types of problems that can be detected. Vibration analysis also has some limitations. For example, it cannot tell you explicitly how long a piece of equipment will run. What it can provide is valuable information that indicates if a problem is getting more severe or not. Vibration analysis also cannot effectively detect operational problems, transient events without special testing, or catastrophic defects that fail very rapidly if continuous data is not collected. Likewise, vibration analysis can be unsuccessful if the user is not properly trained to collect the appropriate data and interpret the results correctly. Overall meters typically measure overall vibration or specialty vibration measurement for spot checks of equipment. They are typically limited in storage capacity. They require little vibration training or knowledge to be used, and typically are used by maintenance professionals or machine operators. They are considered inexpensive compared to other methods of monitoring. Overall continuous monitoring provides real-time monitoring of the overall vibration levels. A common output is a 4 to 20 milliamp signal. This method is very good at detecting changes in condition, however it cannot identify the cause of the change. Once installed, the system can be used effectively with little vibration knowledge. Typical applications are balance of plant to mission-critical assets. This approach is a good compromise of cost, protection, and ease of use. Integrated systems utilize a 4 to 20 milliamp signal to interface with existing control systems to provide real-time continuous monitoring. PLC software can be customized for monitoring and alarming. This system is simple to use and understand. It can be integrated into a data historian system and is easily scalable from a single asset to an entire plant. Portable data collectors are used to collect route-based data on many machines or perform on-the-spot condition assessment. The collected data is uploaded to a computer with advanced software that is used to analyze the data. This collection method can be used on a wide variety of equipment types and provides a snapshot of machine condition. Portable data collectors can provide a good value for the cost depending on the use. Online monitoring systems are typically deployed on mission-critical assets. They provide frequent measurements up to real time that are stored for further analysis using advanced software. Most online systems have automated or rule-based alarming. Online systems can be used for a single asset or deployed across many assets and are commonly used on equipment such as high-speed compressors or large gearboxes. Online systems can be more expensive than other options but provide more protection. Protection systems are used when machine protection is required. Typically, this includes highly critical equipment or equipment that, if allowed to fail, would present a safety hazard. Protection systems typically provide real-time monitoring and have the ability to shut down the equipment based on its condition. Large turbines are the most common application for this type of monitoring. While this type of system provides the highest level of protection, it can also be the most expensive. A common question is, when do I apply each type of monitoring? I like to think of the entire asset base as a pyramid broken into 4 categories. Highly critical equipment that requires protection, mission-critical equipment that can have a significant impact on the business if allowed to fail, balance of plant equipment, which is everything else worth monitoring, and run-to-failure equipment. This is equipment that does not make financial sense to monitor. There are many factors that should go into the decision-making process when determining which category an asset falls into. The idea is to weigh the cost of each monitoring option against the risk if the asset is allowed to fail. Factors to consider include the cost to perform the repair, additional component damage if a failure is allowed to occur, lost revenue during downtime, ease of machine replacement, lead time for replacement parts, lost product in the process when a failure occurs, diminished quality, environmental impact, and of course safety impact. You have just completed Module 1, Vibration and Types of Monitoring. Please join us again for Module 2, Transducer Types and Selection. You can visit us at www.wilcoxon.com or contact us directly at 1-800-WILCOXON.